So we're very happy to have Rama Mishra talking to us. Rama, turn it over to you.
Thank you so much. So I take this opportunity to first wish very happy birthday to Lou Kaufman and also to organizers who gave me this opportunity to present. And after hearing talks from the previous talk was so much high standard, so people would find probably this too light. But anyway, I would like to share whatever I have worked on. So this is about trying to understand weaving knots and their invariants because it's a big family, infinite family, which is parameterized like there are doubly infinite things. So WPQ in general. And if we fix P, then Q also varies. So we have concentrated on W3N. And by asymptotics, I mean how different invariants behave when N goes large. So what is it? Why isn't it moving? My slides are not moving. Um, we- no, I don't know why it's not going down. I'm not going to the next slides.
Yes.
Yeah, there's some glitch in my laptop.
To say stop share and share again.
Yeah, maybe.
Stop.
So just a, huh?
It's paused.
Oh, why is it paused?
Will you click on this one?
Yeah. No, should I? No.
Will you say stop sharing and maybe share again?
Okay.
Yes.
Go-
Try starting over.
Yeah, let me share again because it's
Sure.
not moving.
Yeah, I'll try that again.
Oh, I'm so sorry.
Oh, no
Yeah,
problem.
yeah. This one and do this.
No, maybe double click on that.
Yeah, is it now?
It's
Is
there.
it?
Yeah, your
Okay.
title slide is there.
No, but still it's not going to the different slide.
Oh, we just saw it almost went. It looked like it
Yeah.
was sliding to the left. Yeah, there you go.
Oh, all right. So I understood. It's not the arrow. It's the, I have to just use the touch screen. Yeah,
Okay.
okay. So let me, yeah. So weaving knots, as I explained, they are doubly finite. Again, the talk went off. Where is the talk? I don't know. I can't see the talk. View.
Yep.
I'm just wasting too much time.
It's okay.
Among your tab,
Yeah,
some preview somewhere.
where?
Tabs should be visible. And if you go down,
View.
if you go down,
I somehow want to just go to my talk and not see people.
yeah, just go down. You
Go.
go down further. It's just now
Where?
showing no, below. Where it was showing all of your
Here.
double click on that.
Yes. All right. So how to remove this?
Cannot remove it. Drag it. It's
Okay. Because this is something. Okay. So yeah, there's some green thing coming in between.
can you drag it?
I don't know. Dock to top.
Yeah. If you click on that, yeah.
So weaving knots, as we know that they are having the same projection as torus knots. It's just that they're made alternating, and they have with the braid diagram, so with P strands and N half twists. So they constitute doubly infinite family of hyperbolic knots. And these are some examples, like I've drawn W3, 5, and then with 4 strand, it's 4, 5. And this family attracted interest because it was conjectured that they have maximum volume among all the knots with same crossing number. And keeping that in mind, Champanirkar, Kaufman, and Purcell, they proved the following theorem, that the volume for this family lies between these two, like they found a lower bound and an upper bound. And here this by V oct and V tet, they mean the volumes of the ideal octahedron and the ideal tetrahedron respectively. And they call this bound to be asymptotically sharp, because when you divide the volume by the crossing number, then the limit stabilizes. It's same as the V oct. So this asymptotic behavior, it raises the general question that why not examine the asymptotic behavior of other invariants of weaving lots, because this volume and because of volume conjecture, there is a lot of interest exploring other invariants like colored Jones and Jones polynomial. And so here we have concentrated on exploring Jones polynomial and ranks of Kovenov homology, and also higher twist number, which was introduced by Dasbach and Lin. So in the beginning, I forgot to tell that this work it's a joint work with Ross Stiefelt. So in the beginning, like more than 80% is the joint work with Ross and me. And the last part is with Vivek Singh also, because now we've been working when it comes to finding a closed formula, and that is an ongoing project. So right now what I'm sharing is a joint work with Ross and myself. And here, because we are trying to explore Kovenov homology and Jones polynomial, and this family is an alternating knots family. So Kovenov homology in general, like you can't determine just with Jones polynomial, but for alternating knots, thanks to the Lee's result, that if we know the Jones polynomial and signature, we can compute Kovenov homology. So for this family of knot, we could compute the signature easily, because again, because they're alternating, so the combinatorial method worked, and we could find that for odd P, the signature is 0. And when the P is even, like the family of the form W2K, comma N, the signature turns out to be minus N plus 1. And because of that, the Kovenov homology lies on these just two lines. So for odd P, it's just J equal to 2I plus or minus 1, because signature is 0. And for even P, this is how Kovenov homology will be located. And now weaving knots, there are some more nice properties. First of all, they come as a closure of this P strand braids. And because we know toric braids, we just have to put inverse in between to make it alternating. And for P odd, this family is amphichiral, and that's again easy to see. And for P even, one knows that they are not amphichiral, because for alternating amphichiral knots, Murasagi's result says that the crossing number has to be even, and when P is even, then there will be odd number of crossings, so they can't be amphichiral. And again, these knots are hyperbolic, that also is easy because they are not closure of two braids. And we are just going to discuss relations between coefficients of Jones polynomial and their twist numbers and volumes. So first we'll focus on computing Jones polynomial for this family. So our initial work was, we found a formula for Jones polynomial of this family using Hecke algebra representation. And there the trace was like, first we needed to compute the trace and then normalize it. So we couldn't get a closed form expression. We did find a formula, but the coefficients had some recursive properties. So in this formula, if you could see that Cn0, Cn1, Cn2, Cn1, 2, 2, 1, these are notations given by us, and they are themselves polynomials in T, and they satisfy some recursion property. So these are the recursions for these polynomials. And we can see clearly that these recursions, like in order to find any one of them, one needs all of them for the previous one. So it's not like one of them is just dependent on the earlier one. So it's a mixed recursion. And you solve the recursion. So when we tried exploring finding the closed formula, we could find the coefficients. We could only deduce few of them. So first thing, instantly we could see that the span is 2n, which it should be because it should match with the crossing number. And we could also find the trailing and the leading coefficients to be -1 to the n. And then if you write down the Jones coefficient in this form, we saw that since they are emphichiral, that's symmetric about powers, like powers of T and T inverse. So that also, like the way we computed, it matched with this fact that they're emphichiral. And twist number is sum of the coefficients. So twist number is geometrically defined as minimum number of twists among all alternating diagrams. And it was known that it's an invariant. And Dasbeck and Lin had proved the invariance property, reproved it, and also shown the twist number of this family to be 2n. And from our formula also, we could deduce that the twist number is 2n. And once we know the signature and Jones polynomial, following the scheme of Lee's result, we could compute the ranks of Koganov homology, which was very straightforward. So for instance, like in case of figure 8 naught, we can see that how to do that. So we know the polynomial, then we compute this kh prime evaluated at negative q square. And then after that, when you do, then you find the Koganov polynomial, and the coefficients are the one which would tell you the rank of Hij. So we did it for uh, many W3Ns for various values of n. So here we know how the Ij plane, like I and j are related. So when you draw those two lines, we can see, and you at those Ij coordinate, if we put the ranks, then this is how the Koganov homology plot we could show. And then we can see clearly that this, if n is large, then this would be very hard to make any sense. And also because this Koganov homology rank, they follow night move property. So because of that, one of the lines becomes redundant, because if you know the ranks on one line, we could deduce the rank on the other lines. So asymptotic behavior, if we want to see that how Koganov homology ranks behave. Then we wanted to see the distribution. So we wanted to normalize the data. And this is done by computing the total rank of the Kovenov homology along the line. So we are just concentrating on one line and then taking the sum of all the ranks and then dividing each Betti number by the total rank. And that way we get normalized Betti numbers, which sum to 1. And this raises the possibility of approximating the distribution by a probability distribution. So this was done like our baseline experiment was like, if you want to choose normal distribution, you need a mean and a variance. So it's the standard deviation sigma. So the way we wanted to make a function like this, which approximates. So first we tried finding a quadratic function of this form, which was fitting the logs of the normalized Kovenov dimensions and along the line. So first we have the normalized dimensions, and then we took the logarithm of that and then tried fitting a quadratic. And once we could put the condition that once you have this QNX, then write rho nx to be an e to the power QNX with the exponential, and this should satisfy that the integral negative infinity to infinity should be 1. So this is how we do for normal distribution. And to find that formula, we first wrote down Q and X. When you solve that, you can see from the data that you can compute your mu n to be beta over 2 alpha, and then you can find how sigma should look like. So here, when we equate these two expressions and for the location of the local maxima of rho and x, then the efficient way to obtain the parameter sigma n is to solve this equation, because we want this to be exactly equal to this. So we found sigma n to be 1 over square root of 2 alpha. So here we saw that this for W3n, your quadratic turned out to be this, and here alpha and beta were this, and delta was 10.7. Then when we computed, we found the mean to be 0.5 and variance to be 2.64. And when we tried fitting in this, so these dots are the actual dimension, and this curve is the one that we are fitting it, the function, the normal distribution density function. And then we can see how it's not really very close, but we see that if n is large, it keeps getting closer and closer. So here mu n, every n when we work out, this is again experiment, not a proof. So mu n approaches 0.5 rapidly. So this was something which was of interest. On the other hand, we couldn't see any geometric meaning to sigma n. So we feel that if we could assign something like if we could see any interpretation of sigma n, that would be a nice problem. And now see, if you go to W311, the curve looks like this, and we are trying to get n larger and larger. So we are getting, so somewhat like the values are getting closer to the normal distribution. So this was some of the like our experiment which we ran through Mathematica and Maple, finding those total rank and then the dimensions. Then this was our sigma, the whatever, this standard deviation. So there isn't much correlation. It's getting in larger and larger. Then for the other kind, when n is of the form 2k plus 3, then this is the data that we generated. So when we look at the like analyze the our computation, so plots of Kovenov homology computation, this bell-shaped curve, they appear as envelopes of the plots of the normalized dimension. This led us to conjecture that the standard deviations of the bell curves may be an interesting invariant for the family of knots W3N. Now, we studied Jones polynomial on its own terms. So the reason was because they are alternating family, and when we actually compute using Lee's method, the ranks of the Kovenov homology, the normalized ranks, they are some sort of linear combination of the coefficients of the Jones polynomial. So only if we know how coefficients of Jones polynomial is distributed, and if we can show that they follow for each one, like if we fix W3N and we see the K, because the coefficient of T to the power minus N plus K or T to the power N minus K, those coefficients, because there are two variables now, if we can somehow say that they are binomially distributed, then we can use the fact that the limiting situation, it would be normally distributed. And then the ranks of the Kovenov homology also can be shown to be normally as a proof. So again, we talk about higher twist numbers because twist number only relate to the next, like other than the leading coefficient or the last but one coefficient, their sum of the absolute value, and it relates to the volume. So higher twist number was defined by Dasbach and Lin with the hope that they might give better bound for the volume. So the jth twist number was defined as sum of the absolute value of the, if you go move from the lower to like the j term minus m plus j, and then the n minus j, then sum of these coefficients. So j equal to 1 was the twist number. So jth twist number was defined like that. And we can see that because Jones polynomial has a limited span, so you can't talk about a higher twist number for any value of j. So it would run between, in case of, for instance, W3N, your j can only be between 1 and n minus 1. So then higher, Dashbach and Lin had experimented, they had generated a table for alternating knots with 14 crossings, and they had plotted higher twist number versus volume and seen some correlation. They also did it for non-alternating knots. And both situations, there was some correlation that was apparent, but there wasn't much of like how to go about showing the correlation. So we experimented this for our family W3N because now we know Jones polynomial. So we can see at least their coefficients, even though they are defined recursively, but still we can, for few values of j, we found the closed formula for the coefficients and we could see the higher twist numbers. So we computed second twist number and third twist number, and then we conjectured the other ones through the Mathematica and Maple computations. And then we have, like after working through, we found some of the formulas for twist number. So these are, because here the Jones twist number is just 2 times the coefficient, because the coefficients are symmetrically distributed. So the second coefficient is indeed n square minus n upon 2. So the twist number would be n square minus n, and likewise, so second and third, we have the exact formula, and these are the conjectured formula, which we couldn't really prove it. But then we tried plotting the volume versus these twist numbers. So volume, we could generate the data using Snappy, and twist numbers we could compute for several values of and so for a specific thing, we saw the second twist number for lot of knots, and then the volume for those knots for the different values of n, and we see that there is some correlation. It's not linear, but there is some relation. Third twist number versus volume behaved like this. Then fourth twist number, the plot went like this. Now we wanted to see how to find a better volume for bound for the volume. So Champanerkar's, like Kaufman, Purcell, we call it CKP. So from their result, the volume lies between these two bounds. So there is a gap between lower bound and upper bound. And here, after dividing by the crossing number, the upper bound and lower bound, we can see that there is a gap. So we wanted to see if this can be improved. Can we get a better lower bound and things like that? So we generated data. So how, not directly the higher twist number. So we did this manipulation. So whatever twist number you're taking, kth, take the kth root of that. So like tk raised to the power 1 by k, and divide by the crossing number to n to obtain an expression. So we want to compute, find a constant ck times this, such that the limit becomes finite. So we are trying to manipulate ck so that this limit becomes 2 times v tet. So we found that. So whatever we plot ck times kth root of kth twist number divide by the crossing number, and we are trying to compare this quantity with the bound of Champanerkar, Kaufman, and Pearson. So if we plot these, see this lower, this curve is CKP curve for it's. So the upper one is the your upper bound, which is a horizontal line, 2 times V tet, but lower bound is here. And when we plotted for several twist numbers, our curves seem to provide better lower bound than the upper. They are all like below that. So upper bound given by them are good, but the lower bounds got improved if we try using higher twist number. So we had some of the twist numbers that we could see, that anyway I showed in the table, that these are the coefficients that we can compute, and that was just by solving the recursion and doing a lot of algebra and finding these twist numbers. Now this here, the thing is, after a while, like after second and third twist number, if we want to find the coefficient of t to the power minus n plus 4, generally minus n plus any k, it's not easy to really come up with a closed formula. So then if we want to really study the asymptotics, we need exact formula. So we couldn't move using a Hecke algebra approach to find exactly the coefficients and the closed expression for those polynomial. So we moved to quantum group approach. And this is where, like, our current work going on with Vivek Singh and Ross Steffeld. So the quantum group that is essential for our purpose is UHSL2. It's people are familiar with this, like that gives Jones polynomial, the fundamental representation of this quantum group. Just for the sake of, like I'm just trying to say it. So this is generated by these three elements which satisfy these relations. The Lie bracket HE is 2E, HF is minus 2F, and EF is this. So here, this exponential HH is the formal power series, and e to the power h is usually denoted by q. So this has a good Hopf algebra structure with our co-product given like this, and this is co-unit and an antipode. So these are defined here, and this for computations of Jones polynomial, for that matter, any polynomial invariant, the element that is crucial is universal R matrix. So for this quantum group representation, we have a universal R matrix given in this form, and people are familiar with this Q factorials and things like that. So they are, these R and will give what R hat is. They are, R hat is basically R composed with the flip map. So they are elements of the completed tensor product. And now we define representations of this UHSL2 on free modules of finite rank over the formal power series ring this. If we take L to be a non-negative integer or half integer, and VL be a 2L plus 1 dimensional complex vector space with basis given by E minus L plus 1 going up to L, then VL of H is defined as VL tensor this, and we can define this representation TL. So TL is in general like for L. So TL is for 2L plus 1 dimensional representation, that is VL. So if L is half, then the dimension is 2. So basically T half is the one that is important for us. T half will be two-dimensional representation of UHSL2, and in general TL is defined like that. And this representation is indecomposable because in the sense that this vector space is not a direct sum of non-trivial invariant subspaces, but it is not irreducible. So now we move to finite dimensional representation. So the H-adic quantum algebra is quasi-triangular and it admits the universal R matrix. And here Q factorials are defined like that. Now, if we focus on the two-dimensional, which is V half, and the basis E half and E minus half, then we write down the universal R matrix. So we can see that Q half and R of that is this. So we can determine what our R matrix would look like. And then if we want to write down, basically if we want to compute the Jones polynomial, we need to see the representation and where our braid goes, and then find the quantum trace of that. So weaving braid W3N, it's closure of a 3-strand braid. So we need to see half tensor, half tensor, half. So it would be 8-dimensional, and then it would become very hard to compute the trace and so on, because the matrices will be of larger order. So we decompose it as 3 by 2 direct sum half, direct sum half. So in general, the building block for invariants of weaving knots are R12, R23 inverse. And this looks like this. So we deliberately, instead of writing 8 by 8, we decomposed it in this form. And then that makes, so after that, we know our braid is sigma 1, sigma 2 inverse to the power n. So we need to compute the nth power of this matrix. So we knew that how for n equal to 1 it looks like. So we used some kind of induction argument to find the entries for each n. And this was inductively proved. We guessed it and then we proved it. So how these M11n, M12n, M21n, they look like. And we have a closed expression for that. And then the quantum trace can be computed because they are in the blocks. So you compute it, and then we found the formula for Jones polynomial in the closed form like this. So here, this coefficient T N K, which is like, it would be for power T to the power minus n. So K varies from minus n to n. So you can have Tn minus n. So, and then it will go on up to n. So your T and K themselves have, they are in terms of binomial coefficients. So this became at least manageable, because these things we know what they are. We can compute, even though it might be hard, but we can compute them. So this is the floor function, and these are the binomial coefficients. Now, we needed to, if you want, still like this is not very appealing. So we wanted to give a better expression, some approximate expression for T and K, which helps us showing that the coefficients are binomially distributed. So as far as formula is concerned, we have a closed expression, but our goal is to see the distribution where it fits, so that we can see that as n goes large, how the asymptotics look like. So we tried in terms of generalized hypergeometric series. So this is how a general hypergeometric series looks like. It has like in first parenthesis, you have 4 curly bracket, 4 parameters, then 3 parameters, and then a number. And it should look like this. So here Ci is defined inductively like this. Again, we know they are quantum factorials. So using this, our T and K turned out to be, so the parameters A1, A2, A3, A4 are as follows. So this is A1, A2, A3, and A4, and B1, B2, B3 are K plus 1, 1 minus, N minus K, and B3 is this. And for Z equal to 16, if we see, then we found that T and K turns out to be this. Now, if we need to approximate the coefficients of Jones polynomial, so the first thing is like if we try seeing the sum of the absolute value of the coefficients, it turns out to be in terms of Lucas numbers. So this is well known because there's a result by NAFA. He related coefficients for W3N. So this family has been really very popular. A lot of people have computed invariants for weaving knots W3N, and the polynomial F N K Z, we know the thing that we computed, the hypergeometric series. This is of degree floor n minus k minus 1 by 2. And here the coefficients are all positive. So we try taking the linearization estimate. So try approximating linearly. Then it turned out to be approximately like this. So 2 to the power n plus 1, n times 2 to the n minus n 2 to the power n minus 1 minus n square minus 18n minus 1. And now this, if we try comparing the absolute values of the coefficients that are known with the estimates that we derive from linear approximation, so it compares with the normalized values. Now, if we want to control the estimates, so here we see that this linear approximation is not really very good. It's a relatively poor estimate. So we need to compute. So we were trying to find constant terms. And maybe if we can't really compute all of them, can we see how the constant term looks like? And it's still ongoing that we need to find the distribution of W3N, which compares with the binomial distribution, so that we can, in the limiting case, we can deduce that it follows a normal distribution. And then the Khovenov homology ranks also can be shown to be normally distributed. So that's still like hanging. We need to work on this to be able to say it as a proof that they follow normal distribution. And this is all. Thank you.